Chapter 1. The Dawn of Computation. The journey of computing technology begins with humanity's earliest attempts to quantify and manage information. Ancient civilizations developed rudimentary tools to assist in calculation, notably the abacus, believed to have been invented around 2400 BCE in Mesopotamia. The abacus used beads and rods to represent numbers, enabling the performance of basic arithmetic operations. This simple yet ingenious invention remained in widespread use for centuries and is still employed in some parts of the world today. In the 17th century, mechanical devices began to emerge. Blaise Pascal invented the Pascaline in 1642, a mechanical calculator designed to aid his father in tax computations. This device used a series of gears and wheels to add and subtract numbers. Shortly afterward, Gottfried Wilhelm Leibniz advanced the field with his step reckoner, capable of performing multiplication and division. Leibniz also conceptualized binary code, which would later form the foundation of modern computing. These mechanical calculators, though limited in functionality and plagued by reliability issues, set the stage for automated computing. During the Enlightenment and the Industrial Revolution, a surge in scientific inquiry and technological innovation further spurred the development of calculating machines. In the early 19th century, devices such as Thomas de Colmar's arithmometer gained popularity, becoming the first commercially successful mechanical calculator. These devices were mainly used in business and scientific applications, reflecting the growing demand for efficient computation. Chapter 2. The Analytical Engine. One of the most visionary figures in the history of computing was Charles Babbage. In the 1830s, Babbage designed the analytical engine, a mechanical device that is widely considered to be the first concept of a general-purpose computer. Unlike its predecessors, the analytical engine was not limited to specific arithmetic tasks. It was intended to be programmable and capable of executing a wide variety of operations. The design included key features found in modern computers: a central processing unit, referred to as the mill, memory, called the store, and mechanisms for input and output using punched cards. Though the analytical engine was never completed in Babbage's lifetime due to technical limitations and lack of funding, the conceptual breakthroughs it embodied were monumental. Babbage's collaborator, Ada Lovelace, played a crucial role in interpreting and expanding upon his work. She wrote what is now considered the first algorithm intended for implementation on a machine, earning her recognition as the world's first computer programmer. Lovelace foresaw the potential for computers to go beyond number crunching, predicting applications in music, art, and science. The analytical engine's design was far ahead of its time and remained a theoretical construct for decades. However, it laid the intellectual foundation for subsequent developments in computer science. The notions of a programmable machine and abstract computation would later be formalized in the 20th century, most notably by Alan Turing. Chapter 3. The Era of Electromechanical Devices. By the early 20th century, as electrical engineering advanced, inventors began to incorporate electrical components into calculating machines. Electromechanical devices, which combined mechanical parts with electrical relays and switches, emerged as a new class of computing machines. One of the earliest examples was the Z3, developed by German engineer Konrad Zuse in 1941. The Z3 is considered the first functional programmable computer. It used binary arithmetic and floating-point numbers and could be programmed with punched film tape. Simultaneously, in the United States, Harvard professor Howard Aiken collaborated with IBM to build the Harvard Mark I, also known as the IBM Automatic Sequence Controlled Calculator, ASCC. Completed in 1944, this electromechanical computer was over 50 feet long and used a combination of mechanical and electrical parts. It was capable of performing a sequence of computations automatically and was used by the US Navy during World War II for ballistic calculations. Despite their mechanical complexity and relatively slow processing speeds, electromechanical computers represented a significant step forward. They demonstrated the feasibility of automated, programmable machines and paved the way for fully electronic computing. These devices bridged the gap between the mechanical calculators of the past and the electronic computers that would soon revolutionize the world. Chapter 4: The Advent of Electronic Computers. The transition from electromechanical to electronic computing marked a pivotal moment in technological history. During World War II, urgent demands for faster, more reliable computation led to the creation of fully electronic machines. One of the first was the Colossus, developed in Britain by engineer Tommy Flowers in 1943. Designed for code breaking at Bletchley Park, Colossus utilized thousands of vacuum tubes and could process data at unprecedented speeds. It significantly contributed to deciphering German military communications and had a lasting influence on post-war computing. Across the Atlantic, American scientists were also making breakthroughs. The ENIAC, Electronic Numerical Integrator and Computer, designed by John Presper Eckert and John Mauchly at the University of Pennsylvania, was completed in 1945. With over 17,000 vacuum tubes and a massive physical footprint, ENIAC was the first general-purpose, fully electronic computer. It could perform complex calculations at lightning speed for the era, capable of executing 5,000 additions or subtractions per second. Unlike earlier machines, it was programmable for different tasks, although reprogramming it involved manual rewiring. ENIAC's unveiling captured public imagination and underscored the enormous potential of electronic computing. It marked a paradigm shift from mechanical systems to electronic circuits, enabling much faster processing. Subsequent projects like EDVAC, Electronic Discrete Variable Automatic Computer, introduced the concept of storing programs in memory, as proposed by John von Neumann. This innovation, known as the stored program architecture, became the blueprint for virtually all modern computers. Chapter 5: The First Generation of Computers. Following the success of wartime developments, computer technology entered the commercial sphere during the late 1940s and 1950s. First-generation computers were characterized by their use of vacuum tubes for circuitry and magnetic drums for memory. These machines were massive, expensive, and required specialized environments due to their heat generation and susceptibility to failure. Nonetheless, they marked the beginning of practical digital computation. One of the earliest commercial computers was the UNIVAC-Y, Universal Automatic Computer, delivered in 1951 to the US Census Bureau. Designed by the creators of ENIAC, UNIVAC, I was notable for its ability to process both numbers and alphabetic data, making it suitable for business as well as scientific use. It gained national fame for correctly predicting the outcome of the 1952 presidential election on live television. IBM also entered the market with the IBM 701 and later the IBM 650, establishing itself as a dominant force in computing. These systems were used for military, research, and business purposes, accelerating the adoption of computers across various sectors. Despite their limitations, slow speed, large size, and limited memory, first-generation computers proved that electronic machines could revolutionize data processing. Chapter 6: The Second Generation. The invention of the transistor in 1947 by John Bardeen, William Shockley, and Walter Brattain at Bell Labs was a watershed moment in computing. Transistors, smaller and more reliable than vacuum tubes, quickly replaced them in new machines. By the late 1950s and early 1960s, second-generation computers featured transistors, magnetic core memory, and improved storage media, such as magnetic tapes and disks. These computers were significantly faster, more compact, and more energy efficient than their predecessors. They also introduced the use of high-level programming languages. Fortran, formula translation, and COBOL, common business-oriented language, enabled programmers to write instructions in a more abstract and human-readable form, making software development more accessible and powerful. Second-generation computers, such as the IBM 1401 and the CDC 1604, expanded the role of computing in industry, government, and academia. Real-time systems and batch processing became standard practices. With improved reliability and performance, computers began to be seen not just as specialized scientific tools, but as essential infrastructure for modern life. The era also witnessed the early formation of the software industry and laid the groundwork for computer science as an academic discipline. Chapter 7. The Third Generation: Integrated Circuits and Miniaturization. The next leap in computer technology came with the invention of the integrated circuit, IC, in the late 1950s by Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. Integrated circuits enabled multiple transistors, resistors, and capacitors to be fabricated on a single silicon chip, dramatically reducing size and cost while increasing performance and reliability. By the mid-1960s, third-generation computers based on ICs were beginning to replace second-generation machines. One of the most influential developments of this period was IBM's System 360 family, introduced in 1964. The System 360 line marked a significant shift in computer architecture by offering a compatible line of machines that could run the same software at various performance levels. This innovation laid the groundwork for modern computing's emphasis on compatibility and modularity. Companies and institutions could now invest in software with the assurance that it would remain useful as hardware evolved. Third-generation computers also saw improvements in memory storage and input/output devices. Magnetic disk storage became more widespread, allowing for faster and more reliable data access. Time-sharing systems enabled multiple users to access a central computer simultaneously, greatly expanding the utility of computing in education and research. Programming languages such as BASIC and Pascal emerged, facilitating education in computer programming and broadening access to software development. The increased affordability and power of third-generation systems led to a rapid expansion of computer use in government, business, and academia. Computers became integral to operations in fields ranging from banking to space exploration. By the end of the 1960s, computing was no longer confined to elite institutions. It was becoming a part of mainstream organizational infrastructure. Chapter 8. The Rise of Microprocessors. The invention of the microprocessor in the early 1970s marked the beginning of the fourth generation of computers. A microprocessor is a single-chip CPU that contains all the essential functions of a computer's brain. The first commercially available microprocessor was the Intel 4004, released in 1971. Originally designed for a calculator, it could perform 60,000 operations per second. Although limited, it signaled a fundamental shift. Computers could now be smaller, cheaper, and more accessible than ever before. The Intel 8008 and later the 8080 followed, with vastly improved capabilities. The 8080 became the foundation for many early personal computers. Companies such as MITS introduced the Altair 8800 in 1975, a kit-based computer that hobbyists could assemble at home. Though rudimentary, the Altair sparked the personal computing revolution. A young Bill Gates and Paul Allen developed a version of BASIC for the Altair, founding Microsoft in the process. The affordability and flexibility of microprocessors opened the door for an explosion of innovation. Apple, Commodore, and Tandy entered the market with increasingly user-friendly systems. Apple's Apple II, introduced in 1977, became one of the first widely adopted home computers, featuring color graphics and expandable architecture. These systems brought computing into homes, schools, and small businesses, transforming computers from specialized tools into everyday appliances. Microprocessors also had a transformative effect on industry. Embedded systems, powered by microprocessors, began to appear in appliances, automobiles, and industrial equipment. As chip technology improved, the boundary between computers and other types of machines began to blur. The era of ubiquitous computing was beginning to take shape. Chapter 9. The Personal Computer Revolution. The late 1970s and early 1980s witnessed the true emergence of the personal computer, PC, as a mainstream product. Building on the microprocessor's capabilities, companies began developing complete computing systems for individual use. In 1981, IBM launched the IBM Personal Computer, IBM PC, which used the Intel 8088 processor and ran Microsoft's MS-DOS operating system. Its open architecture allowed third-party hardware and software developers to contribute, creating a vast and rapidly growing ecosystem. The success of the IBM PC led to a wave of IBM-compatible clones, further driving down prices and expanding the market. Meanwhile, Apple continued to innovate with the Macintosh, introduced in 1984. Featuring a graphical user interface, GUI, and mouse input, the Macintosh was groundbreaking in usability. It popularized concepts like icons, windows, and drag and drop, features that have become standard in modern operating systems. Software development flourished during this period. Word processors, spreadsheets, notably Lotus 1-2-3 and later Microsoft Excel, and database programs became essential tools for office productivity. Desktop publishing and early computer games added to the appeal of personal computers at home. The emergence of graphical operating systems like Windows provided more intuitive access to computing's growing power. The PC revolution democratized computing. What had once been the domain of governments, large corporations, and universities was now available to individuals and small businesses. This shift fueled the growth of the software industry, sparked innovation in peripheral devices, and established computing as a central component of modern life. Chapter 10. Networking and the Internet. The late 1980s and early 1990s ushered in the era of networked computing. While computers had become more powerful and widespread, their full potential was unlocked when they could communicate with one another. The development of local area networks, LANs, allowed computers within close proximity to share resources and data. Ethernet, developed at Xerox PARC in the 1970s and standardized in the 1980s, became the dominant LAN technology, offering high-speed connectivity for offices and institutions. Wide area networks, WANs, such as ARPANET, evolved into what would become the Internet. ARPANET's packet switching technology and the development of the TCP/IP protocol suite allowed heterogeneous systems to communicate seamlessly. In 1983, TCP/IP became the standard protocol for ARPANET, effectively laying the groundwork for the global Internet. The creation of the Domain Name System, DNS, in 1984, and the introduction of services like FTP and email further expanded the utility of networks. However, it wasn't until the invention of the World Wide Web by Tim Berners-Lee in 1989 that the Internet truly began to change the world. The web, with its hyperlinks and web browsers, made navigating the Internet accessible to non-experts. The release of Mosaic in 1993 and later Netscape Navigator helped drive the explosion of web use. Networking fundamentally altered the role of computers. No longer isolated devices, they became portals to vast digital ecosystems. Email, chat rooms, online bulletin boards, and eventually social media transformed how people communicated. Businesses leveraged networks for everything from logistics to customer support. The internet began to weave itself into every aspect of modern life. Chapter 11. The Mobile Computing Era. The dawn of the 21st century saw the emergence of mobile computing as a transformative force. While laptop computers had existed for decades, advancements in battery technology, miniaturization, and wireless networking made truly mobile computing feasible. Devices such as the Palm Pilot and BlackBerry introduced mobile email and scheduling to professionals on the go. However, it was the introduction of the smartphone that catalyzed a major shift. In 2007, Apple launched the iPhone, combining a phone, music player, and internet communicator in one device. With its touchscreen interface, intuitive design, and App Store, the iPhone redefined what a mobile device could be. Google's Android platform quickly followed, offering an open alternative that spurred innovation across multiple manufacturers. Smartphones evolved into powerful computers in their own right, capable of tasks once reserved for desktops. Tablets, such as the iPad released in 2010, provided another form factor for mobile computing. These devices became popular in education, entertainment, and business. Combined with cloud services, users could now access their data and applications from virtually anywhere. Mobile computing changed user expectations and behaviors. Always-on connectivity, location-aware services, and touch interfaces became standard. Mobile apps revolutionized industries, from transportation, Uber, to retail, Amazon, to communication, WhatsApp. The mobile era shifted the computing paradigm from fixed location productivity to ubiquitous, personalized, real-time interaction. Chapter 12. Cloud computing and big data. As computing devices became more numerous and mobile, the need for centralized, scalable infrastructure grew. Cloud computing emerged as the solution, allowing users to store and process data on remote servers accessible via the internet. This model offered unprecedented flexibility, scalability, and cost efficiency. Early pioneers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform provided platforms for businesses to deploy applications without investing in physical hardware. Services like Dropbox, Google Drive, and iCloud brought cloud capabilities to consumers, enabling seamless file sharing and backup across devices. Cloud computing also facilitated the rise of software as a service, SaaS. Instead of purchasing and installing software locally, users could access applications like Salesforce, Slack, or Office 365 through a browser. This shift transformed the software industry, emphasizing continuous updates, subscription models, and user analytics. Simultaneously, the proliferation of digital data from social media, sensors, transactions, and logs created the phenomenon of big data. Organizations began leveraging data analytics to gain insights, optimize operations, and predict trends. Technologies like Hadoop, Spark, and various NoSQL databases enabled the processing of massive datasets. Data science emerged as a critical field, combining statistics, computer science, and domain expertise. Together, cloud computing and big data reshaped IT infrastructure and business strategy. They enabled small startups to scale globally, empowered researchers with vast computational resources, and allowed governments to deliver smarter public services. Chapter 13. Artificial Intelligence and Machine Learning. Artificial intelligence, AI, has been a long-standing goal of computer science, but it was not until the convergence of big data, cloud computing, and algorithmic advancements that AI began to achieve practical success. Machine learning, a subfield of AI focused on algorithms that learn from data, became especially prominent. Breakthroughs in deep learning, particularly with neural networks, enabled significant progress in areas like image recognition, natural language processing, and autonomous systems. Tools like Google Translate, Siri, and Alexa became commonplace. Self-driving cars, while still developing, demonstrated the potential of AI to perform complex real-world tasks. Open-source frameworks such as TensorFlow and PyTorch democratized access to AI tools, fostering a global research and developer community. AI was adopted across sectors: healthcare, diagnostic imaging, finance, fraud detection, e-commerce, recommendation engines, and more. Chatbots and virtual assistants began to transform customer service, while generative AI models opened up new avenues in content creation. The ethical implications of AI also became a major focus. Concerns around bias, privacy, job displacement, and autonomous decision-making prompted calls for regulation and responsible AI development. Organizations and governments began forming guidelines and oversight bodies to address these challenges. AI redefined the frontiers of what computers could do. No longer merely tools for arithmetic or data storage, they became intelligent systems capable of perception, reasoning, and adaptation. This transition marked a new chapter in the evolution of computing. Chapter 14: Quantum Computing and Emerging Technologies. Even as classical computing continued to advance, researchers began exploring fundamentally new paradigms. Quantum computing, based on principles of quantum mechanics, offered the potential to solve problems intractable for traditional machines. Companies like IBM, Google, and startups such as D-Wave and Rigetti invested heavily in building quantum processors. Quantum bits, qubits, can represent multiple states simultaneously through superposition, and entanglement enables powerful forms of parallel computation. In 2019, Google claimed to have achieved quantum supremacy, a demonstration that a quantum computer could solve a problem faster than any classical counterpart. Though still experimental, quantum computing holds promise for fields like cryptography, materials science, and complex optimization. In parallel, neuromorphic computing, DNA computing, and optical computing are being researched as alternative models. These technologies aim to emulate the brain's efficiency, exploit biological processes, or use photons for ultra-fast computation. Edge computing, which processes data near the source rather than in centralized clouds, has gained importance with the growth of the Internet of Things, IoT. Devices from smart thermostats to industrial sensors now generate and process data at the edge, reducing latency and bandwidth demands. These emerging technologies illustrate that the evolution of computers is far from complete. Each breakthrough opens new possibilities and challenges, pushing the boundaries of what computing can achieve. Chapter 15: The Future of Computing. As we look toward the future, computing continues to evolve at a breathtaking pace. Innovations in hardware, software, and connectivity are converging to create an increasingly intelligent, interconnected world. Artificial general intelligence, AGI, if achieved, could surpass human cognitive abilities across diverse tasks, posing profound philosophical and practical questions. Advances in brain-computer interfaces, BCIs, aim to directly link neural activity with digital systems, enabling new forms of communication and control. Companies like Neuralink envision a future where humans can interact with computers at the speed of thought. Sustainability has emerged as a critical concern. The environmental impact of data centers, e-waste, and energy consumption has prompted efforts to create greener computing systems. Innovations in low-power processors, recycling, and efficient cooling technologies are steps in this direction. Global digital inclusion is another key frontier. Ensuring that all communities have access to computing resources, education, and opportunities is essential for equitable progress. Initiatives to expand internet access, provide affordable devices, and teach digital literacy are vital to this mission. Ultimately, the future of computing lies not just in faster machines, but in their responsible integration into human life. Ethical design, inclusive innovation, and interdisciplinary collaboration will shape a future where computing enhances human potential, fosters creativity, and addresses society's greatest challenges. From beads on an abacus to the probabilistic dance of qubits, the history of computing is a testament to human ingenuity. It is a journey of abstraction, automation, and amplification, a relentless pursuit of understanding and shaping the world through information.